All right, everybody. So we'll get started. I know everybody's busy this week, so I appreciate you all coming in. This was just a idea, mostly formed by Dr. Sabri, who is haven't heard from everybody based on the project and everything like that. So thought it would be good just to get some conversation going on that. So not only because I'm also interested in hearing about you guys' projects and where they are, just to see if there's any form of collaboration that might be able to happen, within the balance of academic integrity and stuff like that, just to see this is what this person's doing. Maybe they're having difficulties with this thing, or you're seeing some possible avenues and feedback that we can give each other as looking for going along your project. So I didn't have a good idea. If anyone wants to go first or anything like that, just start talking about your project. I was thinking about a structure of how you do it, but honestly, if anyone just wants to talk, it's more of a discussion session today than anything else, and gripes about your project. So that's where we're at. Anyone, any volunteers? Anyone avidly stuck in their research and wants to talk about it?
I can just start based off of this.
Sure, go for it.
So my topic is the quantum effects in psychology, cognition, and neuroscience. And I chose the topic because I like psychology and neuroscience, and I had no idea that quantum mechanics had anything to do with that field. So I'm doing a survey paper.
Okay.
So I'm just going through current research in this area, and there's a lot of it.
Yeah.
So the progress that I've had, I guess the difficulties is, I was gonna reference this book by actually one of the prof's colleagues at IU.
Right.
So he wrote a book on quantum cognition using explaining cognition models using quantum models and probability.
Okay.
So I guess the hard part of that is that I didn't really study probability that much, so I don't have it was kind of tricky to understand that, but
yeah,
I'm going through it slowly, so I think I'm getting it. But yeah, I think the topic overall is very interesting. There's a lot of, I feel from what everything that I've read, it seems whenever there's an area a phenomenon that people don't understand, somehow you can kind of relate quantum mechanics into it, and
right.
Then yeah, so I feel they've done that a lot in different areas of neuroscience and cognition.
Interesting. So they just kind of throw the word quantum at it and be oh, maybe this describes it, because we don't know what's going on.
There's always a reason that they use it, but
okay.
Even one of the critiques that I read about that different people's approach was just because there's two different things that you don't understand doesn't mean that they're always correlated.
Yeah, no, that's a great way to put it. That's actually pretty funny. Yeah.
But it's kind of cool too. The coolest I guess idea that I heard was people don't really understand consciousness that well.
Yeah, absolutely.
One thing that they do understand is that anesthesia, it can dissolve consciousness. That's what they say. That's all they know about consciousness. So people are okay, maybe it's related to quantum mechanics. And then they actually did find something where the electronic spin in your microtubules in your brain, they spin at different rates based on the level of anesthesia you have or something like that.
Huh.
So I guess there is some quantum thing going on.
Yeah, maybe something going on there at that lowest level.
But yeah, it's all very, very new. Even this idea was just literally I was reading an article and it came out in January of this year. So
yeah, wow. Yeah, you're definitely at the forefront of probably our understanding. Like you said, if we don't even understand quantum mechanics, how could we start to correlate it to other things? But yeah, extremely interesting. I think you were the only one in the class doing that sort of field of topic. So, you said you're having some problems understanding and reading at least reading comprehensions, because you're going into fields that you don't necessarily have that much background in. Is there any particular examples where you're oh, I'm reading this paper and it's I don't have no understand this thing or anything like that, or?
Well, the thing is, there's a lot of different areas, and there's experts in different fields that are combining the ideas, right? So for quantum cognition, I was a lot of it is very heavy probability theory and stuff like that. So I didn't know that well, but there's easier to understand examples that they use too. So
okay, all right. Okay. My suggestion, because yeah, you're definitely I mean, all you guys, this is obviously not a very approachable set of topics that you're doing too. Just because you're doing a survey paper doesn't mean obviously you need to go out and understand everything to 100% detail. So it's okay to kind of keep it high level enough for your examples, at least based on what I understand of a survey paper. you don't have to be like, okay, like here are the every minute details and be able to explain everything. And it just like kind of like one of my profs said this one time where it's like you got to capture the image of the paper and then kind of just re-explain that in your survey paper. Because yeah, you're dealing, especially in that topic, something that I'm assuming you didn't do much of your undergrad in. So yeah, absolutely. Wow, that's a lot.
Yeah, I don't even know why I chose a paper because I didn't even write that many papers in my undergrad. So I'm just learning how to write a paper as well.
Yeah, exactly. It's not exactly computer science or software engineering forte. It's more of a research skill. But I mean, if you're ever looking to go into academia, this is all you'll be doing all the time. So it's a good skill to have. Yeah. Anyone else? Any feedback on Yamina's project or anything like that? Anything they at least found interesting?
Any critiques?
I don't know about feedback, but in terms of things I kind of didn't expect. I guess I thought more of the technical side of quantum mechanics, like implementing it, algorithms. I didn't think of it even used in some of that stuff. It was just, it was way past the scope of what I was planning on doing.
I mean, you guys are probably implementing stuff then, right? Like that's cool.
Yeah, no, they all have varied balance, but yeah, it's very cool to see how like quantum branches out into like way other fields, like just almost like at a philosophical level, and then we start like trying to apply it to all these things. It's like a new lens to try and understand the world.
Yeah,
So
there's like a lot of really radical ideas too. I was like kind of surprised that like whenever people start talking about consciousness, I feel like it goes like anything that they say about it, I just am like surprised. Like I don't know if that's real or not.
No, right? Yeah, I'm sure it gets like, yeah, because yeah, even consciousness as like I'm not very well versed on the topic, but just like all I know is that it is very, I don't want to use the word finicky, but it's kind of like almost ethereal. Like we can't pin down like, yes, this is consciousness, but this is not. Like you said in the anesthesiology example, that's like one thing that we're like, maybe this is a line between conscious and unconscious. But yeah, it's a very like contentious topic itself.
Yeah, so I'm like focusing more on like the areas that like make more sense to me.
Definitely.
And there's like I feel like a lot more proof and studies being done in that area. So
Yeah, no, great. Yeah, definitely keep it simple and just the stuff that you can understand and grasp, because you could obviously go and all this stuff is way on the edge of the field of research. So that's great. Okay, that's awesome. Thanks for sharing, Yamina. Anyone else? We don't have to move on, but like also I just want to get through everyone. I know there's only 3 of us here, but Dionysius or Chris?
All I'm doing is a chatting app that uses quantum cryptography.
Oh, interesting.
It's not high scope.
No. That's it's still all of them they're all equally difficult. So do you want to tell us a little bit more about?
Yeah, sure. I wanted to explore like quantum cryptography because like in class we talked about like RSA and stuff like that, and how like it relies only on the fact that computers suck at factoring numbers, and that's like the only level of security basically with RSA. And I wanted to kind of explore like practical applications of quantum safe cryptography, I guess. So like I did that by like I don't really have the messages encrypted right now.
Okay.
I currently just have like a server that just lets you like send messages to each other.
Huh.
But like eventually I just want to have like each client having their own keys and stuff, like with quantum key distribution, and have them kind of communicate that way.
Wow, that's very, very advantageous. Do you have anything like you could show us? Not that you have to. I'm just very curious. Just like you want to.
Super scuffed right
Oh no, honestly, this is not. You're not being marked on this. I'm just like very curious. You can even plug it in here if you want to, just to see. If you don't, no worries. Oh yeah, sure. That works too.
If anyone else wants to come up, I guess I could.
Yeah, no, sure. I'm just like very curious itself.
Like I literally.
Oh, so it's literally running off an HTML page? Okay.
Yeah, no, like I have the server running and everything, like it just sends it off. It's just a WebSocket connection.
Okay.
Like, you just make a username.
Okay.
Sends it to everyone.
Nice.
You can make one here as well.
And so there is actual chat box functionality. So where, at what level is the actual like encryption happening here?
So I guess like between the people communicating.
Okay.
Like if I send a message to D,
You get it on there.
this guy's gonna get it. But this
that's
guy's
really cool.
Interesting. Yeah. No. Awesome.
Like I want to have like a key separate, like a key for each person.
Okay.
And kind of have quantum key distribution that way.
Okay.
So like the messages would go into the server like encrypted, and then to the person receiving the message encrypted as well.
Huh.
And
Wow.
they would try to decrypt it.
Interesting. Okay. So do you have to have a big understanding of like how quantum key distribution works, or?
I don't know about like big understanding because like the methods for quantum key distribution is pretty like solid, like in terms
Okay.
of the algorithm. in terms of like not breaking it.
Right.
And the only way people have found to break it is like attacking the implementation of the quantum computer itself.
Interesting.
So like shining lasers into the computer, you know,
Oh,
like
wow.
at like different intervals, and then somehow they're able to get the different keys that way.
Right. Almost like a laser sniffer of
Yeah,
some kind. Wow.
exactly.
That's
And they were able to get it like 60% accurate or something like that. And the quantum computer usually is able to detect when someone's trying to attack it.
Okay.
But with the way they did it, I'm like, it's again way beyond the scope of my understanding.
Fair. Yeah.
Like the way they were able to do it, like the quantum computer was unable to like detect that someone was trying to attack them.
Oh, interesting. So it wasn't exactly like 100% like we tell that there's an eavesdropper there.
Yeah.
Wow. Okay. Well, thanks for sharing. Sorry. Yeah, I don't want to like make us all stand here, but that is like really interesting.
How do you implement like a quantum encryption? Like is that done?
Right now, like I don't have the quantum encryption. Like I have a translator. Like it's going to be a server, like because we can't have like the clients I have in JavaScript, but like Qiskit JavaScript is not very well supported right now.
Yeah.
So like I want to have like it's kind of like the client is the JavaScript client plus like a Python server that it communicates to. I want to have that be like one entity. Like eventually that's how it's going to be, hopefully.
Okay.
Quantum computers are a thing, but
Like
right now it's just like
you're gonna use like Qiskit and Python to do it?
yeah.
That's so cool.
Yeah. No, that is really cool. Was there easy tutorials to find on like quantum key like version in Qiskit?
Hopefully.
Okay, so we're working on it. Okay, yeah, no, you don't have to. Obviously, it doesn't have to be 100% right now. But wow, okay. So, any significant like challenges besides like being out of the scope of your understanding, like any like implementation details problems that you've run into?
I mean, the algorithm itself seems like relatively simple enough. I guess the only thing that I came across is that the client needs to actually communicate with another backend. So like it's not encrypted that way, like when it communicates with the Qiskit backend.
Right.
It's like you're sending a message there to be encrypted, and then you're receiving a message back.
Yeah. So it's
Right.
all yeah. Okay.
Yeah, because we don't have quantum computers here to actually do the encryption. So,
Yeah, we're kind of all just emulating it. Yeah.
yeah, so it's kind of like an abstraction, I guess. Like I want to have it be seen as just one entity, just like the client communicating with Qiskit.
Yeah, no, honestly, that's fair. Honestly, you don't need to, yeah, because yeah, we're not expecting you to build a quantum computer for the project. It's like we'll just we'll emulate it or just like yeah, abstract it away and say like, oh, this is one thing for now. Yeah, awesome. Well, that's really great, Kinesis. Yeah. Did you say why? You said you were interested in cryptography, so that's why.
Yeah.
Yeah.
Like I wanted to know like the practical applications of it. And apparently like they have already like implemented stuff like this, but it's just like way too slow for something like a chatting app.
Oh, interesting.
It's too expensive. So they do it for like bank-to-bank transfers and stuff, but
Huh.
not for like sending SMS.
Okay. Wow. So yeah, there are already some applications out there. That's really cool. Really cool. Chris, you want to share?
Sure. For my project, I decided to do another like you Qiskit implementation. I guess a mix. I'm doing there's an algorithm in machine learning called K-nearest neighbors. It's just a basic classification algorithm. So I was just trying to implement that in quantum, using quantum mechanics, and then also implement it classically, and just check runtime, see what's better, faster, what's the speed of everything. So far, the hardest problems I found was there's like a lot of papers online, I guess, of people talking about doing it, but they're very technical and they have a lot of math, and then they just like throw a circuit at you and they're like, you can use this, and it's just like I guess conceptually it's hard to wrap your head around. So I'm writing down a lot of just zeros and ones everywhere and trying to figure out how these things work or how they're supposed to look like. But I guess it's really hard to see because you're also doing everything in bits. So calculating distances and everything, they have like special ways that they can do it faster, but it's hard to tell if you're getting it right because of the ways that they're doing it. So that's just been my biggest problem so far. I mean, a little few snags of like trying to get things into big superpositions. So, like the idea is they're putting all your, like in machine learning, in case you guys didn't know anything about it, but they use training sets, right? So you have you train on a bunch of data. So for K-nearest neighbors, they have a bunch of training data, and you put a point somewhere, and then it calculates distances from that new point to every single point in the training set to determine the classification. And so in a regular algorithm, the more points you have in the training set, it's going to take a lot of time to do that. So the way quantum computing does is it takes the training set and it makes it a big superposition, and then does the subtraction with the superposition. So I guess it does all of it at once immediately, and then with a little bit of magic, somehow it pops out your answer. I'm still a little working on the last parts. Everything seems to work to a certain part, and then the answer is a little. I don't know. It's also hard because you get all the bits back, right? And I don't know what bit I'm really supposed to be looking at. Dr. Sabri was helping me, and he just said, "It's the second bit," and I'm like, "What?" So I was kind of lost. But,
Okay.
But yeah, those are some of the biggest things. And then superpositions, you got to deal with creating them. And we didn't, I guess, deal that much with them. We just, if you want superposition, put atom mark. So then
Yeah.
had to figure out how to make superpositions of any number you wanted. So if you want to make a superposition of like 3 and 5, how would you do that? Things. But other than those things, wasn't that bad. Everything's going decently smoothly.
Okay.
But once the quantum part's done, everything will be like so much faster. Like there's probably millions of proper implementations of KNN for classical online, and then I just run them with different test sets and fun. But
Yeah.
biggest thing is just reading the papers. They're very complicated, and they reference other papers that are also complicated. So,
Yeah. No, that's totally fair. You're deep into that's every researcher ever. So I don't understand this. I don't understand what you're saying or what you're referencing.
It's a very big change from like regular programming, where like anything you search for, there's millions of people who've done it, and there's like easy ways to do it. Like there's just one line.
Yeah.
This is like really deep into it. Like there's so much math and everything, and it's just I don't know how Dr. Sabri can read this, but I was reading it and I'm like, I'm so confused. I guess they expect a lot of you to know these things.
Yeah.
Like they just throw in words randomly. Like they'll just be like, oh yeah, take the log t of the most significant bits and you get your cond. And I was like, what the heck is that? And
Yeah, what
they
is
just
that?
never explain it anywhere.
Yeah, absolutely. Yeah, at least in a proper introduction, they should try and explain like as much of the background as possible.
Yeah.
But yeah, they really are writing towards a very, very specific audience, and it's
Yeah.
not an undergraduate student.
Yeah, they all have introductions, but the introductions are so high level. They're just like, here's the idea, and then they jump right into an implementation of something, and you're like,
Yeah.
wait, where else? What's N? What's T? Like I expected a little bit more of like a formal description. N is going to be your number of bits, but they kind of just use it like you should know.
Yeah.
So I was like,
Yeah.
this is a little confusing.
Absolutely. Well, I'm glad you reached out to Dr. Sabri because that is like my number one suggestion. I was also going to say for you guys, if you're ever stuck in like a particular point, you're like, I don't know how to don't understand like X. He's a wealth of knowledge, so he can help. Not with every little thing, but yeah, definitely like some big like pain points. But yeah, that is unfortunately the way. Is there's a lot of assumed knowledge reading any academic papers, especially in this field. So it's going to be a lot of problem getting through that. Do you have anything, if you'd care to share, that like of implementation, like not like actual physical code, or like are you just working through examples right now still?
Right now, I mean, all it is just like you can just see circuits.
Sure, I would love
You
to see
just look
circuits.
at gigantic, big circuits. But I guess it doesn't really mean anything.
No, I still like looking at this.
Like this would be my test point. These 2 bits. Right now, I was a little confused reading the paper of how they do like so I was trying to make an XY plane. So it have 2 features: your X points and your Y points for the algorithm for the AI. But I was really confused how they were doing the superposition. So I just left it with like a straight line, kind of just only X.
Okay.
Only points on X, and so it's kind of very,
Yeah.
very basic.
One dimensional, yeah.
Yeah, 1 dimensional and 2 bits right now, just because I was gonna do 5 at most, but
No,
that seems kind
just
of
start simple, yeah.
Yeah, so and then these would be this A1 and A0 would be your and A2. So A1, A0 is the point of the training set, and then A2 would be the classification of that point, concatenated together, and then you make a giant superposition out of all that.
So what is that? Do you mind if you turn your brightness up just a little bit more? Sorry. What is this like big superposition gate that's right there?
So apparently, Dr. Sabri had a way of trying to make a superposition, which was like you take every single possible thing, then you run it through a UF that if it's in the training set you want, it return a 1, and then you collapse that on the 1, and then you get your superposition. But it was really hard to implement and everything. So he found another way for me. It was using this thing called state vector. You kind of just basically create your own state vector. You tell it I want a a 1 in like this, the 0, 0 bit, and or the 0, 1. You do that, and you just keep doing that. You tell it which ones, and then you make the superposition. So this one, I think, is a superposition of 0 and I don't know what that's supposed to be. If that's a 1.
Is that binary? Is that supposed to be
I think it might be 3 actually, but this is the probability of both those two. Oh, it's because it's 3 bits long. But it's a 0, a superposition of 0, and this should be a 8.
Okay.
Right now, because the classification is concatenated with it. So originally it's 0 and 3, but the classification for 0 is 0, and the classification for 3 is 1. So it just happens to be. But it makes a superposition of those two. This portion does like supposed to do the distance calculation between these. Your t is, so instead of in k nearest neighbors, they use a k, so like 3 neighbors to determine, or you pick a different k, like 5 or 6 or whatever. But the way they did it in this paper, they use a distance threshold, so it's kind of, instead of picking a number of k, you just say, as long as they're within a certain radius, I guess. So I have to make a t, and then an syllabit, and then you do the distance, and then there's this nasty way of trying to figure out, I guess, how like if it fits in the threshold,
Okay.
and it's supposed to just pop out an answer, but I don't know the second bit. Is it like this one or this one? And it's either way, it's not the right answer. So
No.
I'm still working through that.
Okay, so that's totally fair. Wow. So
So
yeah.
far, it looks like it's working. So everything else.
What part of like the algorithm that you're implementing is like the quantum part? Like for the circuit that you showed, will it be like someone like puts in their input and then they'll tell you, like they'll classify it for you? Like
Yeah, so you have a training set of data and the classifications along with it, and then you just put in a test point that you're trying to classify, and it'll classify it for you. So it's the main thing that's doing, I guess, quantum is the superposition, and then it makes use of superposition in for quite a few things. Like it does it for the all the distances. I can't remember what else, but I was also going to use Grover search algorithm, but the implementation I found on this one didn't happen to use it, so I didn't end up. But I guess so mainly superposition is the biggest thing of just trying to see the speed up there. So I think I'll notice it more if I'm gonna do classical and quantum and see like maybe like 5 points and then like 10 points in the test in the training set, and then if I keep getting bigger and bigger, I'm assuming that's when you'll see the speed up, because you'll do less subtractions each time. You'll do one whole thing with the superposition versus like classical would do maybe like 1,000 subtractions, or like Euclidean distances. So I figure that's where the speed up's going to be, but first I gotta figure this one out. So, yeah.
Yeah, that's totally fair.
that's really cool.
Yeah, no, I'm sure a bunch of headache. I had a question because you said like the k nearest neighbors you were using a distance instead of
Yeah.
like an actual sorry, you were saying like almost like a Euclidean distance instead of like a neighbor's distance.
It's the way they do the distance actually not even Euclidean, but it's they basically have a threshold of how far. Like instead of setting a k of the 3 closest, they set anything that's close within I guess a radius of like, let's say like 5 whatever Euclidean distance units is.
Okay.
So that's how they would do that. But they're using some Hamming distance, which
Huh.
I'm kind of confused how it makes sense. But Dr. Sabri seemed to say like, okay, yeah, like it's a proper way. And from all the papers I've read, Hamming distance seems like it's very popular in the quantum realm.
Okay.
I guess because quantum still deals a lot with the bits. So and Hamming distance is a bitwise distance. So like if you just basically check how many bits are different. So if it's like 1, 0, 1, and the other one's like 0, 1, 0, it would be 3 bits different.
Right.
So it's pretty simple. For some reason they did it weird too. But I don't know. I think it's all these kind of like they're doing the bitwise things that make sense, but then they're also adding a bunch of math that they've probably done behind the scenes that makes it a little bit probably faster, but it gets complex when you're trying to read it from an outsider's perspective.
No, that's totally fair. So my question was then, is using the Hammond distance and then say for your classical implementation, you'll use like PyTorch, so like PyTorch dot k nearest neighbors. Like, does it matter that one is using a different distance in the quantum version versus the classical version? Like, is that a fair comparison? I don't know. That's an open question.
I was probably gonna still on the classical try and make it use Hamming distance.
Okay.
Because I did think like the Euclidean distance and everything as much as it's the more regular, because you're squaring numbers and stuff, the overhead that might take for those things might just cause extra time that's not
Right.
really fair. So,
Yeah.
but yeah, that's why I was gonna probably try and stick it to the same implementation or as close as possible.
Yeah.
But yeah, the
No.
biggest headache is just with quantum, you have to do everything in like a circuit. So it's very like, I guess hard. Like you even adding like the big thing at the bottom was just adding two numbers together.
Yeah.
That's all it was, apparently.
Yeah, I mean that's obviously what Dr. Sabri's been talking about. Lectures
Yeah.
trying to get away from this circuit level implementation to a little bit higher level abstraction.
Yeah. It makes sense what he was saying in lecture too, because we were talking about some of the stuff that I was trying to do, and I guess looking at it from a quantum perspective of the superposition or anything, it does give you a different view of it than maybe if you're writing it out just with plain code.
Right.
But it does make it like pretty hard to do simple tasks or simple things. You have to put a lot of gates. You got to figure out how to combine all them together, and then it's just annoying.
Yeah, no, absolutely. Yeah, definitely also probably gives you an appreciation, or at least it would for me, on like, the simple things we do even in Python of, 5 plus 5, and then all the gates that have to, like, the amount of like compilation and just like that level of like machinery that's hidden to us under the gates, just like, oh wow, this is actually a miracle that we can do anything. Yeah, no, that's totally fair. But yeah, very cool as well. So yeah, all your projects are all extremely interesting, also ambitious, each in their own ways. Kind of dissimilar, unfortunately. Like you, Dionysius, and you, Chris, are a little bit on the implementation side. You'll have to do something in Qiskit and Python eventually, I'm assuming. But yeah, I was hoping there would be more like similarities. Like a lot of people are like of the projects are doing post-quantum security. So there's some similarities there, but I guess it was just the three of you guys that showed up.
I was thinking of doing security, but I don't know why I chose this.
That's fair. I mean, they're all extremely interesting because they all have like, like assuming quantum is implemented, extremely big ramifications on like the world at large, like for our understanding to our security to like, how we implement certain things. So like, yeah, extremely important areas that are not well understood yet and not well, like as you've discovered, formalized and like don't have a lot of resources out there yet. So yeah, extremely interesting. Thanks for sharing, guys. Anything else? Any feedback or comments on anyone else's?
Not on anyone specifically, but I was just curious, like if anyone did like other topics that you're allowed to tell us.
Sure. I don't think anyone will be mad, hopefully, about if I like at least what they proposed.
We're not presenting or anything, right? Like, we're not
No, unfortunately you're not. This is like the closest we'll get to like
Yeah.
presenting. So like I'm not sure if Dr. Sabri or anyone will be interested in like sharing the resources, like and like posting them, because I think that'd be interesting to read through other people's work. But yeah, we'll see if that's a thing. Yeah, we had two other people on like post-quantum security. One that was trying to use blockchain security, like with quantum computing, like either from like using Grovers for mining or like actually different like security in the blockchain. Then yeah, we had someone working on the different models of like how you could implement quantum computers. And then, yeah, some others just trying to look into the current state of quantum computing and what, like maybe like look into some of the specifics of error correction or like what you would do in order to get quantum computing to the next level where we can actually build possible quantum computers. So all extremely difficult topics, very hard to broach and very difficult for a very small project. But yeah, that's what I was saying. Like Dr. Sarbi, wants you to include a little bit of technicality, but also like, again, try and keep it high level. And don't destroy yourself over the details because it's all very, as you found out, a lot of very difficult stuff. So, yeah. But yeah, hopefully we can read the other papers because I'd be very interested to see what's out there. So I'm very interested, I don't know about you guys, about Dr. Sabri's, like, not that I could read one of his papers, but reading some of his work and seeing like his stuff on quantum programming languages. It's all sounds extremely interesting, but yeah, very, very like you really need to know what you're doing to be able to read some of those papers. So, yeah. Any other questions or comments? Okay. All right. Well, I appreciate you guys coming out. I don't know if this was helpful at all or not, or at least hopefully interesting just to see other people's stuff. But yeah, I appreciate it, and I apologize for the recording. It's a little bit less readable since we were just more talking and showing stuff. But yeah, thanks again for coming out, guys. And if again, like, feel free to reach out to me, Dr. Sabri, or anything if you have questions, comments, or concerns of the project. But good luck working on the rest of that for the 8th. So, yeah. All right.